Let's move to lecture 4, diffusion mechanism. Um, in the lecture 3, actually, we use the diffusion equation to understand in macro scale. You will know how the concentration of diffusing atoms change with location and time, no matter in steady state or non-steady state. But here in lecture 4, we are more interested in micro scale, how the atoms moves during diffusion process. So first of all, we need to learn how to estimate or calculate the diffusivity D and how the diffusivity link with the atomic movement in materials or crystal structures. So this is the outline in lecture 4. The first section, we are going to talk about the thermally activated diffusion, which means that the diffusion driven by thermal energy. And the second part, we will talk about the diffusion phenomena or diffusion process in crystal lattice. So we are going to introduce several atomic diffusion mechanisms and also in different crystal structure, for example, like FCC, BCC, and HCP. Not only in these metals with different crystal structures, we will also talk about in ionic solid materials. So the overall you need to learn in lecture 4 is just need to understand the relationship between the atomic jumping process versus the diffusivity D. So we start from the first section, thermally activated diffusion, which means that the atomic diffusion process uh, is driven by thermal energy. So I'm going to introduce the atomic jumping process. And then under the random walk or correlated atomic jumping process, what's the relationship between how to correlate them, this jumping process with the diffusivity and under these situations, so this can help us to estimate the diffusivity. Okay. So first of all, we need to give you an introduction starting from the atomic jumping process. If everything is in um, micro scale, right? So this is the atoms, and this is atoms, and what's the thermally activated jump? What we have here is we have series of thermal activated discrete movements between the neighboring positions of local median energy. What this means, this means now you have atoms, and we focus on number 1. The atom number 1 now is at um median energy state. The atom 1 want to move from number 1 position to 2, then to 3. So what's the whole process for this atomic movement or atomic jumping? So this is a cartoon, right? But in real FCC structures, the atoms at location number 1 is shown like this. If you want to jump to number 3 with also the minimum energy state, they need to go through number 2, location number 2, then move to location number 3. But this is like a timing, right? So in order to allow the atoms at number 1 location make a successful jump to number 3, location number 3, then it should overcome the energy barrier, delta E activation energy or activation or energy barrier. This energy can support number 2 to push upper and bottom atoms away to allow it make a successful jump finally to location number 3. The other side with lowest or minimal energy state. So this is how the atoms moves through crystal or in crystal structures. So our target actually is try to link this moving atoms moving process or jumping process with the diffusivity. But I'm going to give you the other examples here. I have atom here, and it start make several jumping, and finally it reach make several jumps. Then after time tau, the atoms moves to here. So this is obviously this process is the diffusion process or atomic jumping process. But because my purpose is going to link the diffusion with atomic jumping process, right? So it turns out after serious atomic jumping, then you can visualize the diffusion really happens. So diffusion is a series of individual or discrete jumps. In order to describe this phenomena, so you can write down like the starting from here and ended here. So the total jumps for these atoms, not, we can call it as n tau, the total numbers of jumps equals to gamma, a jump frequency times the time, diffusion time tau. So gamma actually is a jumping rate, total jumping rate, the total numbers of jumps per second. Then you times the total time, so you will get the total jumps. And for the displacement of each jump, we use a vector of small I. And we sum all the small I together, then we will get the capital R is the total displacement after n tau times jumps. So you sum the vectors for each jumps together, and I starting from R1 to Rn tau, then you sum them together, then you get the vector of capital R we call the total displacement after n tau times jumps. So based on here, you have some ideas. If you want to link the diffusivity with atomic jumping process, you need to know the jump rate, diffusion time for sure, you know that, right? And the small r actually in crystal structure, each jumps were related with lattice constant, right? So based on here, the only parameters we have no idea will be the jump rate. Do you have any idea about the jump rate for atoms or how to estimate it? So it turns out gamma is quite important, right? Because capital R it also is similar list together, and it turns out it related with, and n tau actually equals to gamma tau. So we know that actually you need to know the gamma first. So in order to help us to estimate the jump rate for the atoms, so we move back to page 4. This is a thermally activated jumps. We want to know the jump rate. We're starting from the jumping process. In classical mechanics, the atoms actually vibrate within the this square potential well over a span of L with residence time tau。它在这个是位能井，然后在古典力学里面，粒子是被困在或者是这主要在位能井里面做振动，然后它的距离是 L，然后会 resident time 就是停留的时间是 tau。And this is the location A or like location 1, location 2, and location 3. The activation energy we just mentioned for prior this slide actually is we use the EM or EA to represent the activation energy or energy barrier between the activated state and uh, basic or lowest state. And the difference is EA minus E well. Okay. So the question we just want to know is gamma jump rate, right? Successful jump rate. What's a successful jump rate? So it will be should be the jump from low energy state to activated state, then will spontaneous jump to the other lowest energy state. So how many atoms, even like atoms always like vibrate within the square potential well, but how many atoms have sufficient energy to overcome this energy barrier, which means that have higher energy, higher than EM, or depending on the temperature. With increasing a temperature from T1 then to T2, you can visualize more atoms in T2 can overcome the energy barrier, and the probability can be expressed like exponential to negative migration energy divided by KT. This is a probability. So in order to estimate the jump rate, gamma prime can be successful jump rate can be written as the vibration frequency times the probability of the atoms to cross the energy barrier. Everything we discuss here is ignore the quantum tunneling effect. So successful jump rate depending on the vibration frequency. And probability actually is you just substitute this term here, right? So what's the vibration frequency for the atoms? This is just one dimensional, so along one specific direction. So we use a gamma prime. So this first term actually is a vibration frequency, and the second term is a probability. We just copy this term here. So we will put more. We are more interested in the first term, which is a vibration frequency. Vibration frequency actually can be written as the velocity divided by the distance. So can be written here, and the detailed deviation you can check from the textbook. But it's because the energy here just the thermal energy, so it's related to thermal energy KT. Okay, and and the other, everything is related with this actually is estimated in classical mechanics. And velocity actually the unit, if you it's quite difficult to remember, so I give you some hint. Velocity, the unit is the distance divided by the seconds. We call the velocity. If you times the reciprocal of the distance, then you will get the vibration frequency, because the unit for vibration frequency is the 1 divided by seconds. It's a vibration frequency, the unit for vibration frequency. And this velocity divided by the distance. And some people probably were curious about why the velocity be written here. You can have this thinking. Thermal energy, this is energy, right? And do remember like mass velocity square. So if you want to write down a velocity, should move here divided by m and square root of. So mt divided by m actually is due to here, but it's not that easy. It's just a roughly like concept point of view. So the detail you still have the angular momentum related with that. So you have 2 pi here. So this is just roughly, just help you to remember here. But this is in classical mechanics. But some people consider that the most important assumption for classical mechanics is let's know any interaction between atoms. But in reality, the atoms in crystal structures, they do have some interactions through the bond, no matter covalent bond, hydrogen bond, or any type of bond, right? So classical mechanics doesn't works for under these situations. So some people use the quantum mechanics to modify the atomic vibration frequency, and which show in the potential be modified as a parabolic potential well. But under these situations, the vibration frequency be rewritten like here, and this actually be derived from in the harmonic oscillation model. By the harmonic oscillation model, you can derive the atomic vibration frequency. Okay, so give you a quick review here. This is a harmonic oscillation model. The difference, the difference between this model with the classical one is they do believe there's interactions between two atoms. This interaction actually be considered as a spring. So two atoms attached by a spring, and we can use the spring constants to represent the interaction between two atoms. So this is more similar with the atoms inside crystal structures. So based on here, we can we can estimate the vibration frequency for the atoms and show like this, and will be proportion with this is a force constant related with the bonds, different types of bond and also bond stiffness divided by m is the reduced mass related with the mass 1 and mass 2. So we use this idea and back to here. So we use the beta instead of the k here, but reduce mass here. So here you know that the mu is a vibration frequency. So now you know that the specific direction, I mean the jumper ray, gamma prime in specific directions will be affected by the beta is a force constant, spring constant, or bounce related with bounce strength and the reduced mass for the atoms, and also migration energy, and also the working, I mean environment temperature. So if you want to increase the jump array, which means that you can either increase the bond strength, reduce the uh, atomic mass, or you also can lower the migration energy or increase the working temperature. This is what you can do. So all this, it turns out you can speed up the diffusion phenomena, right? So this is a gamma prime. Okay, so after I mean in the following slides, we are going to use this model to interpret the gamma